Question 3 was the last question in the bonding and structure longer answers, and no doubt some of you found it a little bit challenging because it's quite an open question, or it appears to be an open question, kind of like an essay style question. These are becoming a little bit more common, particularly with AQA, I've noticed, over the last few years. But in reality, if we really looked at what it's asking us to do, and we stop panicking about the fact that it says 10 marks, we're looking at 3 compounds, so we probably want to average 3.5 marks per compound. So actually that's not so scary. If an individual question says, tell me about the bonding and the physical properties of sodium oxide, tell me about the bonding and physical properties of carbon dioxide, and so on, you wouldn't be so scared if you saw a 3-mark question, and you don't have to write quite as much as you think. Having said that, this is A-level, and this would be a style of kind of the level of response question, and so it's likely you may have to write a little bit more than 3 things for each one. So we're just going to make sure we cover all of it, and we're going to talk about bonding and structure. Remember, those are 2 separate, slightly different words. Okay, the easiest thing, although it's as discussed, is simply to do each compound in order. In fact, you could even do a table for this question and it would still work. So physical properties. Remember melting points and boiling points. Conductivity is going to be part of our physical properties. And we may talk about solubility, but melting point, boiling point and conductivity are the main areas that we can link to the strength of the bonding and everything else. So we're going to try and write them all in the same format so that we don't tend to miss things out. You don't need long sentences for this. We don't need a lot of because and wherefores and howevers. So we'll start with sodium oxide. Hopefully we're aware that that's an ionic compound. So our bonding is ionic. And if it's ionic, our structure is a lattice. As simple as that. Yes, there are some compounds which are ionic liquids and they're not a giant lattice structure. Will you have to write about them at A-level? No, so don't worry about it. So, what can we talk about a giant lattice structure that is ionic? We can describe what the ionic bonds are. So they are electrostatic attractions between oppositely charged ions. So we're actually describing that, and we can link that to boiling point. So electrostatic attractions between oppositely charged ions in a giant structure is going to lead to very strong bonds. So strong bonds on its own isn't going to help unless you've said what they are, and we have. We said they're attractions between oppositely charged ions. Then we're going to link that to energy, because bonding doesn't relate directly to melting point. High melting point comes from the amount of energy needed to break the bonds. So I'm linking it all together. Notice I haven't really done great sentence structure. It's not sort of compulsory. Conductivity, it would conduct when molten or in solution, and it would dissolve because it's sodium oxide. We might want to talk about solubility, but we definitely want to explain why it conducts, that the ions are free to move. So we haven't gone too far on from GCSE, but then again, this was probably sorts of questions that were at the higher end of GCSE anyway. So I would then go to carbon dioxide, and I'm going to have plenty to say, again, just talking about the type of bonding, the type of structure, and how that relates to the properties of carbon dioxide. So bonding is covalent, but the structure would be simple molecular. Carbon dioxide and silicon dioxide are often compared, especially by OCRB. So what's that going to relate to? It's going to relate to low boiling points and melting points. In carbon dioxide, I'd probably focus on the boiling point because it's a gas Sodium oxide, I'd probably focus on the melting point because it's a solid to start with, and that's related to weak intermolecular forces, which require very little energy in order to break them apart, break the molecules apart. Now, you could identify the intermolecular forces. The intermolecular forces in carbon dioxide are simply instantaneous induced dipoles. But when you are comparing 3 different types of bonding and structure rather than comparing different molecules, it's not necessary that you have to identify the different forces involved. No conductivity in any state because there's no ions that can move around. There's no delocalized electrons. In brackets, we could say it does dissolve in water if we really wanted to add a little extra information. The reason it does that is because it can hydrogen bond with water, and we mentioned that in the intermolecular forces video when we looked at the different examples of when hydrogen bonding can occur. And then last compound that we need to look at is silicon dioxide. Silicon dioxide is one that students often forget as our example of giant covalent structure. So my bonding is covalent, but my structure is giant. Most students really focus on graphite and diamond when they're thinking of giant covalent lattices, and therefore they sort of forget about silicon dioxide. So still in group 4, still able to form a large covalent network is the other way it's described in some exam boards. So we are now talking very high melting point. I want to distinguish that from the high melting point of sodium oxide because it's probably going to be 2000 degrees more. Very strong covalent bonds. So we are now saying, we're talking about the strength of the bonds, but we're also labeling the bonds. We're being specific that we have to break covalent bonds in order to melt silicon dioxide. A lot of energy to break and no conductivity in any state. Again, there are no charged particles that can move around. All the electrons are used in bonding, and there are no ions that can move around either because it's a covalent substance. So we can add to that if we want to explain why something doesn't conduct. We could have also added this to carbon dioxide. There's no free moving electrons or ions. No solubility either. And the reason it's not soluble in any solvent is because we can't break apart those covalent bonds. There's no solvent that could break covalent bonds and move that lattice apart. So you can see actually we wrote 3 paragraphs there to get 10 marks. We didn't really need to write huge amounts in order to get everything, and more than likely there'd be more than one thing that you could say. For example, I realised looking back on this that I could have talked about the solubility of sodium oxide. So I could have said it's soluble in polar solvents such as water because the water forms bonds with the ions or forms ion dipole attractions. So I could have added that in as well. But actually remember that quite a lot of the time you might be getting 2 marks simply for identifying covalent and simple molecular. So by the time you've done that for 3 compounds, you've already got 6 marks out of 10. So don't panic when you see something that looks like a large essay style question. You can get 6 marks out of 10 simply by being able to identify what bonding and structure is present in a compound.